Okay, I just thought of one, it came up in the discussions, one other little side issue I didn't mention. I probably should have put in a slide on it. We've really been dealing with the very austere model problem of the Hodge-Laplacian. What if you have variable coefficients, for example, or lower order terms? Usually that's not a big deal, and I just want to point out it's not a big deal here also. So first let's talk about variable coefficients. So we have the same terms here, dd star and d star d. But well, for example, instead of div grad u, we might have div a grad u, where a is a vector or is a function or a matrix, bounded above and bounded below. Of course, that should make things very much more difficult. And that's absorbed in the current theory without any additional changes. Here I wrote down how we've been writing the Hodge-Laplacian. Find sigma in L2 lambda k minus 1, and also such that d of it's in L2 k minus 1, h lambda k minus 1, u in h lambda k, and you have these L2 inner products here. That's the problem we've been solving. Instead of L2 lambda k, whose inner product is the integral of u interproducted with itself. That's it. It's the integral of that. We could put a weight in here, and we could use an a sub k here, or it could actually be a matrix weight aku dot u, if this a is bounded above and below, and we could have a different weight on each. So maybe I'll put the weight down here. So it's a weighted L2 space with a different weight. So we get to choose 3 different coefficients here, one for k minus 1 forms, one for k forms, one for k plus 1 forms. The space is the same, the topology is the same, but there's a weight in it. That doesn't change anything. And so we still have a Hilbert complex. The same elements we used before still work for this one. And now you write this all out and you have an operator with a bunch of variable coefficients in it. In fact, all 3 of those come up as coefficients in Maxwell's equations. So if you're going to do Maxwell's equations where the permittivity and the dielectric constant and so forth depend on space, then you would need to make use of this. By the way, my advisor, he was always interested in oil problems, so nonlinear problems. He used to say, well, variable coefficients are not of much importance, but when you have a nonlinear problem, then the linearization of its variable. So they're really an essential thing to do a nonlinear problem where the coefficient depends not only on x, but on the solution, which depends on x. So we certainly need to be able to handle variable coefficients, so it's nice to know it's no problem. Yes? Yes, so when we apply the Hilbert space theory, we define WK is equal to L2 lambda k weighted by the A inner product. I don't know how you write that. It's the weighted L2 lambda k. So if the space is L2 lambda k and the WK norm is defined to be this, that, and H lambda k is the same as before, except that when you defined its norm, the norm on it would be u in WK plus du in WK plus 1, and these have weights in them, and everything is exactly as before. And now what about lower order terms? Well, for example, if you wanted to add a plus cu here to that equation, that would correspond to be something here where you had some coefficient LUV here. Now it's not a different Hilbert complex because this term doesn't appear in the Hilbert complex. This is not of the form du dv. It's just a lower order term. And you have to check whether that affects the analysis, or you can prove that these lower order terms don't affect the analysis. And so I have a student named Larry Lee, and I had him look at that, and he's looked at all 5 places where you might have a lower order term. So basically he's looked at, now let's get rid of the variable coefficients and just look at the lower order terms. D plus L1 of D star plus L2 of U plus D star plus L3 of D plus L4 of U plus L5 of U equals F. And basically, you can handle all those terms. They're no big deal. Similar things had already been done for mixed methods for the Poisson equation. So that's not a major issue. So here, A would be would be a symmetric positive definite operator from alternating K forms to alternating K forms in this case. So there's no big surprises in that business. Any questions? Okay, so final topic I want to talk about is fairly recent work. We've been working on it for quite a while on finite element differential forms on meshes of cubes. So there are two main families that I know about. I'm not 100% sure that there are not other ones to be discovered. Actually, some days I think it's quite possible, and other days I think it's unlikely. I'm not sure. But the two major families, one is long known in some sense, maybe not quite in this context, but the ideas were all there, and then one is brand new. So the one that's long known is nice, and I think it's one of these things that thinking about it in finite element exterior calculus context helps make it clearer, and that's the tensor product construction. So suppose I have two different domains, omega and omega prime. And I have some subcomplex of the de Rham complex on omega. So this is D. If I have to be very careful, I'll say D sub omega. And I have some subcomplex of the de Rham complex on omega prime. Some other subcomplex, so I guess I need primes here. Well, I don't know if that prime implies this prime. Maybe it does. Okay, and now what I want to do is I want to sort of take a tensor product of these complexes, whatever that means, so that I get a subcomplex of the de Rham complex for omega Cartesian product omega prime. So, which would be an RA, n plus n prime. So actually it turns out that there's a well understood way to take the tensor product of two complexes. Forget about whether they're differential forms or anything. And so suppose we have a complex, V0, V1, etc. And we have another one, W0, W1, etc., with its own D, dW and dV. How would I take the tensor product of these and get some other complex with some other differential built out of these two? Well, if you go back way back to homology 101, we said another way to think of a complex was as a graded vector space, sum over I of the VI's. That's our complex. And we have a map, dV, which is a graded linear map of degree 1, so it takes VI into VI plus 1. Okay, graded degree 1. And we have another one of these for W. Okay, well, so now when I want to take the tensor product of them, I want to come up with a graded algebra, a graded vector space, sum over K, Well, what am I going to do? Tensor product is bilinear, so I'm going to get pieces vi. So here I'm going to get the sum over I and j of vi tensor vj, wj. And I want to sort of collect them by k, which goes from 0 to infinity. So I collect the ones where I plus j is equal to k. And that's the space that I would call V tensor W K. So this thing is the sum over K of V tensor W K. Those will be the spaces of my complex. So the tensor product of complexes gives you another, well, it's going to turn out to be a complex where the pieces are sums of tensor products over different degrees. So this is the definition. And then we have to define, how do you define the D operator? So what would be the D V tensor W? That's supposed to take this guy here, sum over I plus j is equal to k of VI tensor Wj, and it's supposed to get you into things where L plus M is equal to K plus 1. VL tensor Wm. So the first thing you see is you don't do the first thing that comes to mind. You don't define D of V tensor W of V tensor W to be D V of V tensor dW tensor W, which would say D of V tensor W is equal, or D of VI tensor Wj is equal to dVi tensor dVj, Wj. That's not the right definition because it gets you into the wrong space. This would get you into Vi plus 1 tensor Wj plus 1. And so that would be part of the tensor product at 2 levels higher. So the correct definition, and what's more, that's not going to work very well with what we want to do because we like D's to satisfy a Leibniz rule. So what we're really going to use, so this is wrong. What we're really going to use is that if we have, say, a V tensor W, where this is in VI and this is in Wj, and now we want to know how to define the differential of it, then we're going to do it as dV tensor W plus or minus V tensor dW. And this would be in VI plus 1, and this would be in Wj, and this would be in VI, and this would be in Wj plus 1. So the whole thing, well, both of these are of the degree 1 higher, so this is in V tensor W I plus 1, I plus j plus 1. If this is in V tensor W I plus j. Right? Very nice, elegant construction of tensor product of complexes as a complex. I suspect it's -1 to almost surely -1 to the I, because you move past I things here. But remember in the beginning I told you I wasn't going to always get them because I'll make a mistake. This might be one of those moments. I'm pretty sure that's it. Now we're not done because we want to apply that construction to 2 de Rham complexes, and at the end we don't just want a complex, we want a subcomplex of the de Rham complex on the Cartesian product space. So I have to interpret what we mean by this definition in the cases where the VI's and the WJ's are spaces of differential forms on omega and omega prime. So I'm going to call the space here lambda k of omega cross omega prime. This is going to be what the tensor product construction of complexes gives us. Except now I want to get this to be differential forms. So let me sort of start to write it in, and we'll sort of do what we have to do. So I have this, which is a space of differential forms on omega, differential I forms on omega, and a space of differential J forms on omega prime, and somehow I want to combine them in a bilinear fashion so I get differential K forms on omega cross omega prime. Well, the Cartesian product comes with a map. I don't know if pi, use of pi's a lot, but I'm going to use it here too. It's a different pi, which is just the projection on the first component. Pi omega of xy is equal to x. And we have also one for pi omega prime. So I can pull back differential forms on omega by this map to differential forms on omega cross omega prime. So I do pi omega star of this. And I can pull back these omega prime forms using pi omega prime. And now these are both differential forms on omega cross omega prime. So I can wedge them together, making this a bilinear operation. And now this is an I plus j form. This is in here. It's in lambda I plus j of omega cross omega prime. Of course, this looks sort of abstract now. There's so many symbols up there. How do you remember what all this means? But it's not really terribly difficult. I guess I'll explain it mostly through the examples. But let's just understand this pullback. Suppose I have a point. So here's omega cross omega. So here's omega. Here's omega prime. I take the Cartesian product. I get something that looks like this. This is omega cross omega prime. And I have the projection operator, which takes something here and drops it down to here. So here's a point P and pi omega P. This is omega and omega prime. So if I have a differential form here, it takes a point on this curve and a tangent vector and gives me a number. Now suppose I want a differential form here. So I take a point on this curve and I have a tangent vector in the tangent space of this. Well, the point, of course, I'll just go down to this point using the projection. And what about the tangent vector? I need to come up with a tangent vector to this line. Well, that line corresponds to a tangent direction in this space. So this vector might not be aligned with the omega direction. So you just project it down into the omega direction and apply this guy. That's the pullback. So it's not too difficult. Okay, so let's see. So what this means is if I have some space of finite elements on one domain and some space of finite elements on the other domain, I can combine them in this way and get a space of finite element differential forms on the Cartesian product domain. And the D operator, by that construction over there, the D operator will just be the D operator in this domain because of Leibniz's rule. This mimics Leibniz's rule. And so the D operator we get is exactly the usual D operator on differential forms here. So now I have a new complex, lambda 0 h of omega cross omega prime by the D on omega cross omega prime to lambda 1 h omega cross omega prime, etc. So let's go to the examples and make it a little bit clearer. Oh, I didn't say anything about degrees of freedom. So what about degrees of freedom? Suppose I have something that's in the dual space of this and something in the dual space of this. Can I combine them to get something in the dual space of that? For that, you don't use a Leibniz rule or anything. You just take the tensor product of the 2 degrees of freedom. So you apply one of them to the first and one of them to the second. And you have to apply it to the pullback so they're in the right places. If we have shape functions on the 2 pieces, then this gives us a construction of shape functions on the Cartesian product. And if we have degrees of freedom for the 2 spaces, this gives us a definition of degrees of freedom for the product. And now let's look at the example. So let's start with the simple 1 degree finite element de Rham complex of degree r. So all that means is on an interval, take polynomials of degree r functions, and take the derivative, which gives you polynomial degree r minus 1 functions, and take as your degrees of freedom the values at the endpoint, and say the integral over the interval for these functions. So when we assemble it, we get continuous piecewise degree r, which is h lambda 0 or h1 finite elements. And here take the degrees of freedom just to be interior to the element. So when we assemble it, we get discontinuous piecewise degree r minus 1. So here's a case of r is equal to 2. Continuous piecewise quadratics to discontinuous piecewise linears. Now, tensor product that with itself. So we have the interval, and we have that space on it, and we have another copy of the interval, and that space on it, and we're going to come up with a space on the square, the interval cross the interval. And the functions are going to be this, well, for the 0 forms, they're just going to be the tensor product of the 0 forms. So here's the 0 forms, the tensor product of the 0 forms with the 0 form. So this is lambda 0h, lambda 0h, and lambda 0h of the square is going to be just lambda 0h tensor lambda 0h of the interval. And so we're going to get the usual Q1 finite elements. And these degrees of freedom are exactly the tensor product degrees of freedom, where you apply you apply the evaluation operator of the first component, and the second component gives you evaluation operator at the corner. The integral over with respect to the first component, but evaluation of the second component gives you the integral over the edge, and so forth. So this is just the usual space Q1, which is the tensor product of P1 continuous with itself, all biquadratic functions, functions whose are at most second order in each variable separately, and have those degrees of freedom. But the next case is a little bit more interesting, because lambda 1 h of the square is defined to be the sum of 2 things. One is lambda 0 h of the interval tensor lambda 1 h of the interval, and the other one is lambda 1 h of the interval tensor lambda 0 h of the interval. That was the definition that the of the tensor product of complexes. So we have 2 kinds of things, which means that we have different kind of polynomials for the first component and the second component. Well, let's write down what we have here. So here we have a 0 form, like a P in PR. And here we have a 1 form, like a Q dx or dy, since it's in the second position, where the Q is in PR minus 1 discontinuous. So we multiply these together, tensor product them, so P of x, Q of y. And we get that dy. And then we also get some S of x dx. So it's S of x, T of y, dx, because we tensor product in S in PR minus 1, S of x dx, with a T in PR. So what does that say? That says that the first component, if we do a vector proxy, so we have a dx, the first component is degree r minus 1 in x, but degree r in y, and the second component is degree r in x, but degree r minus 1 in y. So it's all sort of captured in this picture. Oh, and what are the degrees of freedom? Well, the degrees of freedom were, let's see, in the picture here I'm drawing the lowest order case. So we're really talking about this and this. So degrees of freedom would look like, this is integral along the edge evaluated at the left. So that would be this integral and this integral. That would be one kind of degree of freedom. The other kind of degree of freedom would be the ones we get from tensoring this way, and that would be tangential derivatives in this direction. So we would have 4 degrees of freedom, which would be the tangential derivatives in the edge, and the space would be things which are degree r minus 1 in the first component and r in the second component for the first component of the vector field, and degree r in x and degree r minus 1 in y for the second component of the vector field. Okay, sometimes that space is called Q01 cross Q10. It should really be plus Q10. Same thing. And then in the third case, you have to have both indices sum to 2, and you only have zeros and ones. So the only thing you can do is take lambda 1h tensor lambda 2h. And so you get a single component, which is a p of x, q of y, dx, dy, from the p of x dx and the q of y dy, where p and q are both constants in the lowest order case, or degree r minus 1. So we get the space of discontinuous constants out of that. So this is what happens if we take the tensor product of the lowest order case of this sequence with itself. And this, and also the higher analog ones with R, these were in Ravi-Artoma's original papers. They talked about, well, they weren't doing a whole sequence, they were doing this space here. And they talked about, well, they rotated everything 90 degrees, so for those were PR in the first variable, PR minus 1 in the second for the first component, and vice versa for the second component. Okay, so this tensor product creates these Ravi-Artoma elements, and you can do it in 3D as well, and then it creates the cubic version of the Nedelec edge elements of the first kind. And that was in Nedelec's AD paper, where he did the Nedelec elements. Dmitry. Correct. There's no problem using different polynomial degrees. So you could certainly take the tensor product, say, of this complex with the, say, this complex down here. So this is P2, P1, and P1, P0. And let's say for the 0 forms, you would obviously get what the picture is telling you. That would what you get for the 0 forms. By the way, there's also no problem. So you can use any things that work on omega and any complex that works on omega prime. You could take the case where omega was in 2D with triangles, and omega prime is in 1D, intervals, and then you're going to get prism elements. Like that, and things like this. And so forth. So prism elements come out of this. So that's pretty fully understood. And what I want to talk about for the rest of the lecture is the second family of finite element differential forms on cubes, which we're now calling SR lambda k of IN. And these are not tensor product constructions. And the definition is entirely on this one slide, but it ain't the first thing that pops into your mind. So I have to give you shape functions and degrees of freedom. And I'll try to motivate these a little bit. And just tell you what the key results are. And the key tool was definitely the Kazul operator again. So first of all, I need a definition. So the PR lambda k of anything is spanned by monomials. And so what does a monomial means? Well, first of all, there's an alternator, dx sigma 0 through sigma k. Why did I? Dx sigma 1 through sigma k. And then you can multiply it by polynomials. I'm not using barycentric coordinates here, so just x0 to the alpha 0 through xn to the alpha n. So this is what I would call a form monomial. So it's a differential form with a monomial coefficient. Okay, so some definitions is the degree of this monomial is called the degree of the form. So if this is omega, the degree of omega, by definition, is the degree of this form, which is the sum of the alpha i's. Alpha, sum of the alpha i's. Okay, so the degree of form monomial is the degree of the coefficient. But now I have a funny definition. That one's an obvious definition. Now this is sort of a funny definition. If we didn't have any alternators, we would find the linear degree of a monomial is you just count how many variables enter with a power of exactly 1. Enter linearly, not constant and not higher degree. So the linear degree of x squared y z cubed, L degree is equal to 1, because it's linear in y, but it's not linear in anything else. Okay, but for form monomials, the definition of linear degree is a little more complicated. You don't count the variables that occur among the sigmas. So L degree of omega is the number of alpha I that are equal to 1, such that alpha I is not one of the sigmas. It's a definition, sort of combinatorial in flavor. And so, for example, if I wanted the linear degree of x squared y z dy, it would be 1 again, because I wouldn't count y, because that shows up over here. I'd only count z as a linear. Okay, with that definition, we define this space HRL lambda k. Well, we'll start with HR lambda k. So this is the span of the four monomials, K4 monomials, with degree equal to R, homogeneous degree R K-forms. And now if I put a comma L here, that means and L degree is greater than or equal to L. Linear degree is greater than or equal to L. Okay, so I can define that, and that's a way, if I put L is equal to 0, I get all homogeneous degree R4 monomials. L equals 1, I only get a subset of them. L equals 2, a smaller subset. Okay, and then there's this definition in the next two lines, which defines our shape functions, which, as I say, if you see, and if this popped into your mind, you're way ahead of us. It took us a long time to find this definition. So what we do is we take, these are going to be things we're going to add to PR lambda k. So these should be polynomials of degree higher than degree R, because we already have all of PR lambda k in our space. And so if you take R plus L minus 1, and L is at least 1, this is a homogeneous polynomial of degree R or more, k plus 1 form. And you hit it with the Kazul operator kappa, so it's a degree R plus 1 or more k form. So this is certain homogeneous polynomial of degree R plus 1 k forms, and when we add them to PR lambda k, we get additional stuff. So it's just like for the PR minus spaces, we take a PR space and add some extra Kazuls. We're going to add these ones. But that's not enough because that doesn't give us a complex. When you take d of that, you don't get into the equivalent space one level higher. To give it a complex, I'm going to, well, I need that the previous space like that, when I hit it with d, is contained in this space. And so I just add these, d of this same space, only at the level r plus 1, k minus 1. And these are also of degree greater than r. So it's extra stuff. And what's more, there's no overlap between this middle piece here, JR, and this piece DJR, because JR is all kappas, and DJR is all Ds, and we know there's no intersection between Ds and kappas. Nothing can be both a D and a kappa unless it's 0. So we have a direct sum of PR and certain kappas, which are higher than degree R, and certain Ds, which are higher than degree R. And that's our shape function space. Now, why that crazy definition? What was guiding us? What was guiding us is we knew what we wanted for the degrees of freedom. The degrees of freedom are incredibly simple as opposed to those incredibly unusual looking shape functions. So here's the degrees of freedom. You just take u, you restrict it to the face, or a trace there if you like, and you weight it by just ordinary polynomials. And the degree goes down, but it doesn't go down by 1 every dimension, it goes down by 2. Polynomials of degree r minus 2. And of course they have to be d minus k form so you can take the integral. So we were guided by what's called the serendipity finite elements, which are long known, probably early 70s. Where the degrees of freedom, the serendipity people said, well, if we were to take the tensor product elements, so we get Q1, Q2, Q3, and so forth, they start to be pretty large pretty soon. And well, the suggestion was to drop out this middle degree of freedom here and take a space that has those degrees of freedom. You have to find some test function, so you have to find a subspace of Q2 that's contained something, a subspace of Q2 for which these are unisolvent. And then you have to show that that subspace, so that's called S2. So S1 is equal to Q1. But S2 is contained in Q2, and it contains P2. P2 is only 6-dimensional. This is 8-dimensional. This contains that 8-dimensional space and two other things in such a way that we can use these degrees of freedom, and that's enough so we still get H1 continuity. Then the next one looks like this. And you get S3, which is contained in Q3 but contains P3. But the next one does not look like this, which you might think is the pattern. 3 degrees on side and nothing in the middle. And the reason is if you did that, it wouldn't contain P4. If you want it to contain P4, you need 1 interior degree of freedom. And this contains P4, but is much smaller than Q4. Q4, this has, so let's see, this is the 4-node quad, the 8-node quad, the 12-node quad, and I think this one, what is this one? It's 4 times 4, 16, 17-node quad. And this one would be 25, so it's quite a bit smaller. And in those days, that mattered a lot. The next one, maybe you can guess now, as you go up in dimension, you go up 1 in the polynomial dimension in each side. So these were nothing on the sides, linears, quadratics, cubics, and now we have 4 on each side. And this was nothing in the interior, nothing in the interior, nothing in the interior, constants in the interior. Now we go linears in the interior. That would be the next one. And so you see that what you have is polynomials of degree r minus 2d. You had to go, so let's write it out. We have, so if this is r is equal to 1, we have the vertices, and we have r minus twice 1. If r is 1, 1 minus 2 is negative, so nothing on the edges. The next one, we have the vertices, and then we have 2 minus 2, so we have constants on the edges, one thing on each edge. And then, so this would be the vertices. Verts would be PR. The edges would be PR minus 2, and the squares would be PR minus 4, and that gives you this picture. So the constants don't appear until you get to P4. Okay. So these serendipity elements, these are found in textbooks, in the engineering textbooks. Almost all of them actually introduce these things. Not too many talk about 3D, and the ones who do talk about 3D only give the lowest examples. So of course there's Q1, which is not interesting because it's just the usual tensor product. So that could be called S1 is equal to Q1. The next one has 1 degree of freedom per vertex and 1 degree of freedom per edge. So that's called the 20-node brick. And the next one has this picture on each face. So if I remember right, it's a 35-node brick. And nothing in the middle of the faces, and nothing in the interior. And there is no next one in any of the books that I know. This is basically the story they have. And when they write down the shape functions, say it's the span of the following functions, and then they say it's pulled out of the air, and then they say it's very serendipitous that somebody was able to find them and show that they're unisolvent. There's no indication of a pattern. That's why they call it serendipity. Well, we wanted to keep this structure of going down by 2 in the degrees of freedom each time, but we wanted to find out the pattern for the shape functions so we could continue in 3D and do it in ND and also do it for K-forms. And so we were sure for well over a year that this was the degrees of freedom. And then we slowly, by calculations, arrived at this. And then we did a bunch of computer calculations up to, degree 7 elements in 6 dimensions, and were convinced it was unisolvent, and then struggled to find a proof of unisolvence based on Kazul operator and so forth. Yeah?
The goal is to saturate the polynomial space of total degree?
No. So if you're on any mesh, you're on your mesh, the approximation properties depend on the full polynomial space PR that you contain. Total degree polynomials, not in each. You want to have, so you need to have this space contain P4, otherwise it won't give you an order 4 method in H1. On the other hand, you want to have enough degrees of freedom so that you'll have H1 continuity from here to here. Basically, you restrict this function to the edge, it's going to be a P4, and so you need 5 degrees of freedom on that edge. And the question is, well, you could do that if you take the whole tensor product. Can you get away with less? That was the question the serendipity people asked.
Well, there's a question that I should have asked. So why go through all this trouble? Because if we do it on simplex, then everything would be so natural.
Yeah, so I sort of mentioned before that, it's sort of religious whether you like quads or simplices. I believe that everything is much more natural in simplices. And so I prefer simplices, and in my own computations I use them. But there are people who like them. And you must admit that, for example, the room we're built in seems to have surfaces that are parallel to the x, y, and z axis and would be easily meshed with a cube. The windows have been meshed with squares and so forth. So from that point of view, with man-made objects and so forth, it's not unusual to see cubical meshes. What's that? Yeah, so I mean, they map well into cache of computers and so forth, but they're not as nice mathematically. Okay, so then where we are is we simply had this definition. It's just that crazy space and the simple degrees of freedom. And we get some properties of them. And one of the nice things is the properties are completely universal. They work for any dimension, any degree, and any form degree. And so first of all, the space we defined, SR lambda k, it contains PR. And it's not contained in PR plus 1, but it's contained in PR plus n minus k. So you have a few extra degrees that you add. For the zero forms in 2D, oh, yeah, there's a special thing that actually, in that case, you can actually reduce this by 1. So it looks like it's contained in PR plus 2, but it's actually contained in PR plus 1. In 3D, it's contained in PR plus 2. Then there's an inclusion property, which actually you would think this would be the most trivial thing, that SR lambda k is contained in SR plus 1 lambda k. But it doesn't follow immediately from this definition. But it's true. So it has to be proven that SR lambda k is contained in SR plus 1 lambda k. Now this one is obvious. It was sort of by construction. And this is really, this guided the construction a lot. Remember the unisolvents proofs I gave. They're all induction on dimension. And you can see that's going to be what the story is here, because a serendipity on a cube, if you restrict it to a face, you get a serendipity on a face. We wanted that property, and we got that property. We designed it to have that property. Not only for the shape functions, but for the degree of freedom. So the trace on a face of a serendipity SR lambda k is a serendipity SR lambda k on the face, and the degrees of freedom are obviously, when you restrict them, become the degrees of freedom on the face. Then, of course, we need the subcomplex property. D of SR lambda k is contained in, these are one of these complexes that go down, SR minus 1 lambda k plus 1. By the way, I'm not sure if I pointed out when we had the tensor product elements, it's one of those subcomplexes that don't go down. The R space goes to the R space, goes to the R space, like PR minus. This is more like PR. The R space goes to the R minus 1 space, goes to the R minus 2 space. Okay, then using the first 4 properties, you can give the unisolvents. The proof, as I say, for us was not easy. And actually, we had to enlist the help of combinatorial colleagues at one point. But we could prove that the number of degrees of freedom is equal to the number of the dimension of the space, and we could prove if all the degrees of freedom vanish, then the function vanishes. So we have unisolvents. And finally, the degrees of freedom are exactly what you need to get commuting, unbounded, of course, commuting projections into this complex. So this is a new complex on cubes of finite element spaces. Starts with the serendipity elements and then gets these new spaces. So what are these spaces then? Well, already the case of zero forms is, as I say, it was known in 2D. It was only known for low order cases in 3D, and I don't believe anybody had thought about it for higher D. So I can rephrase the space to make it a little more concrete for zero forms. Instead of talking about the linear degree, I talk about sort of the opposite of the linear degree, the superlinear degree, the degree ignoring the linear variables. So it's the difference between the ordinary degree and the linear degree is the superlinear degree. So x cubed yz squared, just count 5, don't count the y. And then for a polynomial, the superlinear degree is the maximum over all its monomials. And so this is a different way that you could take that definition that we had here, and you read it carefully in the special case, k is equal to 0, and you get that the space we described, SR lambda 0, is just all polynomials of superdegree less than or equal to r. So let me stop there and think a little bit, what does that mean, all polynomials of superlinear degree less than or equal to r? Because this is a definition that should have been in every textbook on finite elements that does serendipity, but it's never appeared before as far as I know. So let's do 2D. So we want superlinear degree is less than or equal to r. 2D, we're talking about x to the a, y to the b. And we want the degree to be the sum of a and b less than or equal to r, and you don't count it if either a or b is 1, you don't count that one. So first of all, we get all of PR, things whose whole degree is less than or equal to r. But then we get two extra guys. We get x to the ry, because the superlinear degree is still less than or equal to 1, and we get xy to the r. And so if we take the span of these two guys and add it to PR, that's SR. Okay, and this was long known. This is how the serendipity elements are described in books. They say in 2D, you could just take PR and you just add two more functions, and x to the ry and xy to the r, and those are unisolvent for these degrees of freedom. So like here we have P1 plus x squared y and xy squared. And here we have P2 plus those guys, and that's the right dimension and unisolvents. 3D, we get SR is PR plus the span of a bunch of things. First of all, we have things like, I'm allowed to go up to a degree r, so I could take anything of degree r. Well, first of all, I could take x to the r, y, z. I wouldn't count either y or z. And so this would be degree r, and there's three of those, x, y to the r, z, and x, y, z to the r. But there's some more. There's any polynomial of degree r, x to the a, y to the b, z, where a plus b is equal to r. There's similar things with y and a z, and x as a special variables. So these ones are degree r plus 1, and these ones are degree r plus 2. So SR in 3D is PR plus a bunch of things, you can count them, of degree r plus 1 plus 3 things of degree r plus 2. And as I say, this definition, as far as I know, was not known before, but it coincides with what is known in the lowest order cases. And okay, there's the two-dimensional picture. And here's the three-dimensional picture. And once again, the first three spaces are in textbooks. This one, I'm not sure, you may see it sometimes. I'm not sure, and I'm sure you don't see above that. And you didn't see any pattern. And here's the dimensions of the spaces in 1, 2, 3, 4, and 5 dimensions. The S2, 1, 2, 3, and 4 dimensions, S1, S2, S3, S4, S5. And what you see is for the large ones, like if we're talking about S5 in 3D, PR is only 56, but QR is 216, more than 4 times as large. But this one is only like 30% larger, 74. And it's even more, if you go to 4D, it's even more so. So these spaces are significantly smaller than the PR spaces. More interesting are the other spaces in 2 and 3D, the 1 forms, the 2 forms. The 3 forms are not very interesting. They're pretty obvious. But the 1 forms and 2 forms in 3D or the 1 forms in 2D are new spaces as far as I know. So you notice when I talked about the PR and the PR minus spaces, all of these spaces had been more or less found before. They were either Nedelec's first kind or second kind. Sometimes there were small improvements to them. But it was sort of like a periodic table where we put things that were known. Here, there were a lot of holes in the periodic table, and they're getting filled in this way. So here are the serendipity 0 forms, S2 and S3. And then this space here, this maps to, this was a known space. This space is, the degrees of freedom were surely known. These were the Bretzi-Douglas-Marini elements, the square version. I'm not sure were the shape functions known for that. It'll probably say here. And then the last space you get is the space of piecewise constants and piecewise linears and so forth. The P spaces, not the Q spaces. And here's the cubic space, and these spaces, the 1 forms and the 2 forms, none of them were known, as far as I know, don't appear in any variant that we found in the literature. Okay, yeah, so here's what I have to say about them. So let's look at the case of 1 forms and 2 forms in 3D. The 1 form is a new element for H curl. We haven't seen a suggestion of this H curl element, although it's the lowest order case is a pretty obvious degrees of freedom, but nobody knew what shape functions would work with that. And again, the 2 form is also pretty obvious degree of freedom. And Bretzi, Douglas, Marinian group, maybe Fortan was involved with that, had tried to create an element with these degrees of freedom, but they didn't find any decent shape functions. And actually, the shape functions they proposed, these are in Bretzi's book, the shape functions they proposed are very ugly because if you turn the cube around, you switch x and y, you get a different space. It's not invariant under that obvious symmetry. And they comment that, well, they don't know quite how to do that, and maybe you could try these or these, but they hadn't found shape functions for this. The next edition of Bretzi Fortan's book will have these elements, I'm pretty sure. And finally, let me just put it in traditional finite element language. This is what I was telling you. This is in the introduction of our paper. If you didn't know any finite element exterior calculus, I could describe this. Cubic elements to use for H1, Hdiv, H curl, and L2 in 3D. So for H1, use polynomial shape functions whose superlinear degree is at most R. That's this new way to describe serendipities. For 1 forms, you use vector fields for which each component is a polynomial of degree at most R, and then you add certain things of higher degree, and what are they? Well, they're of this special form, x2, x3 times the difference of w2 and w3, x3, x1, difference of w3, w1, x1, x2, difference of w1, w2, where the wi's are polynomials of degree r minus 1 and don't depend on xi. Wi doesn't depend on xi. And so if you figure that out, this is a PR minus 1 plus 2, so this is a PR plus 1. So you take PR, you add these special kinds of PR plus 1s, and then you also add the gradient of things whose superlinear degree is at most R plus 1. And this is a space for which the obvious degrees, or the fairly simple degrees of freedom we had, are unisolvent. And you see this space is invariant under switching x and y, and it's stated in an invariant sort of way. The space for Hdiv is slightly simpler. It's basically polynomials of degree R vector fields, and you add the curls of these previous guys so that you have an inclusion in there. And the space of L2 is just PR. So it's something that you can easily write down and implement, and this is now a family, and that's the 3D case, and it works in all dimensions. And I believe that's the last slide.